Okay, so today we're going to go over the probability chapter. We'll start with some definitions, events and outcomes. The result of an experiment is called an outcome. An event is any particular outcome or group of outcomes. So a simple event is an event that cannot be broken down further, and the sample space is the set of all possible simple events. So let's look at basic probability. Given that all outcomes are equally likely, we can compute the probability of an event E using this formula. We have the probability of event E is the number of outcomes corresponding to event E divided by the total number of equally likely outcomes. So example 1, if we roll a standard six-sided die, describe the sample space and some sample events. The sample space is the set of all possible events, which is we can get a 1, 2, 3, 4, 5, or 6. Some possible examples of simple events. We may roll a 1, we may roll a 5. Some compound events. We could roll a number larger than 4, or we could roll an even number. So if we roll a six-sided die, calculate the probability of rolling a 1. Well, there's only one way we can roll a 1, and there's 6 possible outcomes. Okay, again, the probability of rolling a number larger than 4. Well, how many numbers are there larger than 4? That would be 5 and 6. So there's 2 out of 6 possible outcomes. Now we could reduce this fraction to 1/3, but unless it specifically says to do so, I would leave it like that. And typically in probabilities, we deal with fractions and not decimals. So let's say we have a bag with 20 cherries, 14 sweet and 6 sour. If you pick a cherry at random, what is the probability that it will be sweet? Well, how many sweet do we have? We have 14 sweet out of a total of 20. That's it. Again, you could reduce it, but unless it says so, there's not really any reason to. Compute the probability of randomly drawing one card from a deck and getting an ace. Okay, a standard deck is 52 cards. There are 4 suits, each with 1 ace, so there would be 4 aces out of 52 cards. Okay, so some more concepts here. An impossible event has a probability of 0. If it's impossible, it can never happen. So there's 0 chance it'll happen, so the probability of it happening is 0. A certain event has a probability of 1. Again, we're sure it's going to happen, so the probability of it happening is 1. So this brings us to the probability of any event must be 0, which is less than or equal to the probability, which would be less than or equal to 1. So essentially, if you get an answer for a probability that's larger than 1, you've made a mistake. Or if you get an answer for a probability that's less than 0, you made a mistake. And this does happen quite frequently, so be careful of that. The complement of an event is the event E does not happen. So here we use the notation E with a line over it to show the complement of an event. We can compute the probability of the complement using the probability of the complement of E is equal to 1 minus the probability of E. Furthermore, the probability of E is equal to 1 minus the probability of the complement of E. So if you pull a random card from a deck of playing cards, what is the probability it is not a heart? Well, there are 13 hearts in the deck. The probability it is a heart, that would be the probability of a heart. It's 13 over 52. So the probability that it's not a heart is equal to 1 minus 13 over 52. And 1 is 52 over 52 minus 13 over 52, and we get 39 over 52. And that's how that works out. Okay, the probability of two independent events. Independent events. Events A and B are independent events if the probability of event B occurring is the same whether or not event A occurs. In other words, no matter what happens with event A, the odds of event B happening is going to be the same. So suppose we flip a coin and roll a die, and wanted to know the probability of getting a head on the coin and a 6 on the die. So what's the probability of getting a head on the coin? Probability of a head is equal to 1/2. And what's the probability of getting a 6 on the coin or on the dice? Now, the fact that we got a head or not on the coin doesn't affect this. These are independent events, and that probability is 1/6. And as we'll see in a bit, the probability of getting a head and a 6, given that the events are independent, is equal to probability of a head times the probability of a 6, which is equal to 1/2 times 1/6, which is equal to 1/12. So, are these events independent? A fair coin is tossed 2 times. The 2 events are first toss is a head, second toss is a head. Does the fact that we have a head on the first toss affect the second toss? No, so they are independent. The 2 events: 1, it will rain tomorrow in Houston, and 2, it will rain tomorrow in Galveston, a city near Houston. Well, this is kind of tricky here. Depends on how you think about it. Typically, if it rains in one city, it's going to probably rain in a city next, so we'd say they're not independent. But if you live in Florida, you've probably seen where it can rain on one side of the road and not the other. So, again, that one's a little out there as far as how to determine it. You draw a card from a deck, then draw a second card without replacing the first. So, the first card from the deck, let's just say probability of getting a king. So for the first card, the probability would be 1/52 to get a king. That's the probability of getting a king, 1/52. Or 4/52, sorry. Because there's 4 kings in the deck. Then you draw a second card. Now, what's the probability of getting a king? Well, it could be 4/51. It could be 3/51. Either way, it's going to be different based on what happened with the first card. So those are dependent events. So here we come to what I just mentioned earlier. The probability of A and B for independent events. If events A and B are independent, then the probability of both A and B occurring is the probability of A and B equals the probability of A times the probability of B, which is what I did earlier. Where probability A and B is the probability of events A and B both occurring, probability of A is the probability of event A occurring, and probability of B is the probability of event B occurring. If your drawer has 10 pairs of socks, 6 white, and 7 t-shirts, 3 white, if you randomly reach in and pull out a pair of socks and a t-shirt, what is the probability both are white? Well, the probability that the shirt is white is 6 out of 10. Probability of a white shirt. Probability of a white t-shirt, or white sock, sorry, is 3/7. So the probability of white and white is the probability of a white sock times the probability of a white t-shirt, which is 6/10 times 3/7, which is 60 over, not 60, 18 over 70. And that's how that's done. Let's look at another example. Suppose we flip a coin and roll a die, and I wanted to know the probability of getting a head on the coin and a 6 on the die. Didn't we just do that? Yes. So let's rewrite this. Probability of head is 1/2. Probability of 6 is 1/6. So probability of a head and a 6 is 1/2 times 1/6, which is 1/12, just like we did before. Okay, probability of A or B. The probability of either A or B occurring or both is equal to. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So suppose we draw one card from a standard deck. What is the probability that we will get a queen or a king? Well, the probability of getting a queen is simply 4 out of 52. The probability of getting a king is simply 4 out of 52. What is the probability of getting a queen and a king? Now, this is a little tricky here. We're only picking one card, so there's no way it can be a queen or a king. So that is 0 over 52. So in this case, the probability of getting a queen or a king is equal to the probability of getting a queen plus the probability of getting a king plus the probability of getting a queen and king. And this was 4 over 52. And this was 4 over 52. And this was 0, not plus, minus. Have to be careful with these formulas. Now, they will be given to you on the exams. Minus. And we add that up. And we get 8 over 52. So let's try one that makes a little more sense. Suppose we draw one card from a standard deck. What is the probability that we will get a red card or a king? The probability of a red card. Now, hearts and diamonds are red cards. There's 2 suits. So there's 13 times 2 or 26 red cards out of 52. And as we said, there is 4 kings, so that's 4 over 52. Now, what's the probability of getting a red king? Well, there's 2 red suits, which means there's 2 red kings. So that's 52 over 52. So the probability of a red card or a king, you have the probability of a red card, that's probability of a king, minus the probability of a red king. So here we have 13 over 52, plus 4 over 52, minus 2 over 52, and this is equal to 15 over 52. Okay, so example 12. Table below shows the number of survey subjects who have received and not received a speeding ticket in the last year, and the color of their car. Find the probability that a randomly chosen person has a red car and got a speeding ticket, has a red car or got a speeding ticket. So we're going to want the probability of a red car, and probability of a ticket, first of all. So our total number is 665. So both of these are going to be over 665. What's the probability they have a red car? How many red cars do we have? 150? What's the probability they got a speeding ticket? Well, we had 60 of them. So A, red car and a speeding ticket. The probability of red car and ticket. Now let's look back, check what A and B is, just to be safe. That's P of A times P of B, so we get probability of a red car and a ticket is the probability of a red car times the probability of a ticket, which is 150 over 665 times 60 over 665, which is 9,000 over 442,225. Again, you can reduce that, but it doesn't say to, so we won't. Next up, we have probability of a red car or a ticket. So this is probability of red car plus probability of a ticket minus probability of a red car with a ticket. So we need probability of a red car and a ticket. So we have a red car, we have a ticket. We have 15. That's 15 over 665. So probability of a red car is 150 over 665. Probability of a ticket is 60 over 665. Minus the probability of a red car got with a ticket, 15 over 665. And this is 195 over 665. And again, no sense reducing it if we don't have to. There's a lot of issues with rounding error or division errors when you reduce. So if it doesn't say reduce, why take the risk of making a mistake? The next concept we come to is called conditional probability. The probability the event B occurs given that the event A has happened is represented as P given A, or probability of B given A. This is read as the probability of B given A. What is the probability that two cards drawn at random from a deck of playing cards will both be aces? So we have the probability the first card is an ace, and the probability the second card is an ace, given the first card is an ace. So the probability the first card is an ace, there's 4 aces out of 52 cards. Probability the second card is an ace, given the first card is an ace. Well, we now only have 3 aces, and we only have 51 cards. So the probability of ace is equal to probability of ace times the probability of an ace given we had an ace. So this is 4 over 52 times 3 over 52, which is 12 over 2,704. Okay, find the probability that a die rolled shows a 6, given that a flip coin shows a head. Well, what's the probability that a coin shows head? That's 1/2. Now, what's the probability that we get a 6 given we got a head? Matter. These are independent events, so 1/6. So probability of a 6 given a head on the first is 1/2 times 1/6, which is again that 1/12. Let's go back to our car. Same deal. So Find the probability that a randomly chosen person has a speeding ticket given they have a red car. So we know they have a red car, and we're looking at 150. What's the probability they have a ticket given a red car? Well, since we know they have a red car, there are 150 total red cars. And the probability of getting a speeding ticket, well, there's 15. That is 15 out of 150. And let's look at B. What is the probability that a chosen person has a red car given they have a speeding ticket? Well, in this case, there's 60 speeding tickets, and 15 of them are red cars. So 15 out of 60. And that's how this can change just by the way you look at it. Same data, different way. Okay, conditional probability formula. If events A and B are not independent, then the probability of A and B is the probability of A times the probability of B given A, which we've already kind of looked at. So if you pull two cards out of a deck, what is the probability that both are spades? Well, so let's let event A be first card to spade. And the probability of that is 13 out of 52. Now what's the probability that the second card's a spade given the first one is a spade? Well, there's only 12 spades left out of 51. So the probability of A and B in this case, since they're dependent, the probability of A times the probability of B given A has occurred. We have the probability of A, 13 over 52, times the probability of B given A has occurred, which is 12 over 51. So we have 13 times 12, 156 over 52 times 51. 2652. That is it. Okay, if you draw two cards from a deck, what is the probability that you will get the ace of diamonds and a black card? So we want a probability of getting the ace of diamonds, which is what, 1 over 52. And we want the probability of a black card given we got the ace of diamonds. So how many black cards in the deck? 2 times 13 is 26. The ace of diamonds is not one of them, so we have all 26 of them. However, we only have 51 cards remaining. So the probability of an ace of diamonds and then a black card, we have a probability of ace of diamonds times probability of black card given we got an ace of diamonds, which is 1 over 52 times 26 over 51, which is 26 over 2,652. And yes, that will reduce, but we're not going to worry about that. Okay. A home pregnancy test was given to women. Then pregnancy was verified through blood tests. The following table shows the home pregnancy test results. Find the probability they're not pregnant given that a positive test result. So again, we're given positive test results, so we're looking here. Probably not given positive. Okay, well, there were 75 positive tests, and 5 of them were not. That's it. And B, probability positive test given they're not pregnant. So we know they're not pregnant, which is 19 of them, and 5 had a positive test. And that is it. Okay, we will not be doing Bayes' theorem. It's way more complex than you guys need to get into. And that brings us to counting. So suppose at a particular restaurant, you have 3 choices for an appetizer: soup, salad, or breadsticks. 5 choices for a main course: hamburger sandwich, quiche, fajita, and pizza. If you're allowed to choose exactly one item from each category for your meal, how many different meal options do you have? So let's look at this. We have 3 choices for appetizer: soup, salad, and breadsticks. Now we have 5 choices for the main dish, which is what? Hamburger, sandwich, quiche, fajita, and pizza. Now this would be the same for all 3 of these. So we have 5 meals here, 5 meals here, 5 meals here, for a total of 15. However, we have a rule called the basic counting rule, which will make this a little easier. If you are asked to choose one item from 2 separate categories, where there are M items in the first category and N items in the second category, then the total number of available choices is M times N. This is sometimes called the multiplication rule of probabilities. So let's look at this. Well, we had 3 appetizers. We had 5, and 3 times 5 is equal to 15. See, it works. Now let's look at this example. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read? Well, it's simply 21 times 18. 378. Now, suppose a particular restaurant you have 3 choices for an appetizer, 5 choices for a main course, and 2 choices for dessert. You're allowed to choose exactly one item from each category for your meal. How many different meal options do you have? Well, we had 3 times 5 times 2, which is 30. So essentially that rule can extend to more than 2. A quiz consists of 3 true or false questions. In how many ways can a student answer the question? Well, how many ways can they answer the first one? True or false? So 2. How many ways can they answer the second one? Again, 2. How many ways can they answer the third one? Again, 2. And that is 8. Okay, now we're going to move on to permutations. How many different ways can the letters of the word math be arranged to form a 4-letter word? So let's look at this. We have M-A-T-H, we have M-T-A-H, we have M-T-H-A, and we have M-H. T-A, and we have M-H-A-T, and we have M-A-H-T. Next, we would start with A, and if you go through this process, C-H-M, A-T-M-H, A-H-T-M, A-H-M-T, A-M-H-T, A-M-T-H. Again, we have 6, and you'll see that we have 24 ways. 6 ways for each letter starting. This brings us to something called factorial. So this is denoted this way, n factorial. And it's equal to n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1. So this is how this works. Let's go up here real quick. We determine this is 24. Another way to do this would be 4 factorial, which is 4 times 3 times 2 times 1, which is 24. So let's look at another example here. How many ways can 5 different door prizes be distributed among 5 people? Well, 5 factorial. 5 times 4 times 3 times 2 times 1, which is 120. Charity benefit is attended by 25 people and 3 gift certificates are given away as door prizes. One gift certificate is in the amount of $100, second is worth 25, and the third is worth 10. Assuming that no person receives more than one prize, how many different ways can the 3 gift certificates be awarded? Now, you have 25 people, so we're going to give out the top prize, $100. How many different people can get them? Well, all 25 of them. Now we only have 24 people because you can't win more than one prize. So how many people are going to be able to get the second prize? Well, 24 of them. And now the third prize, again, so we're looking at 23. And we have 25 times 24 times 23, which is 13,800. Okay, now again, we have 8 sprinters who made the Olympic finals in the 100-meter race. And how many different ways can a gold, silver, and bronze medal be awarded? Well, giving away the first prize, how many different people can get it? One of the 8, right? And the second prize, well, the guy who came in first can't come in second as well. So that means there's only 7 possibilities. And third prize, there would only be 6. And 8 times 7 times 6 equal to 336. So now we're going to talk about permutations in detail. And this is not correct. This is NPR, same as this. There's a typo in there. We say that there are NPR permutations of size R that may be selected from among n choices without replacement when order matters. That's the biggie. When order matters. We express this result more simply using factorials. Equal to n factorial over n minus r factorial. So I have 9 paintings and have room to display only 4 of them at a time on my wall. How many different ways could I do this? Well, we know that n is equal to 9, and we know that r is equal to 4. Now, does order matter? Well, yes, because let's just look at paintings 1, 2, 3, 4. But couldn't I also display them like this? And that would be a different display. So order matters. The order they're put in the display matters. So we are talking about permutations. Looking at NPR is equal to n factorial over n minus r factorial. So we have 9, and we're choosing 4. So we have 9 factorial over 9 minus 4 factorial, which is 9 factorial over 5 factorial. Now, you may have a calculator that will calculate factorials for you. If you don't, this can be done like this. 9 times 8 times 7 times 6 times 5 factorial all over 5 factorial. And what happens, this 5 factorial and this 5 factorial can be divided out, and then we have 9 times 8 times 7 times 6, which gives us 3,000 24. Example 30. How many ways can a four-person committee, president, vice president, secretary, treasurer, be selected from 16-member board of directors of a nonprofit organization? So we have four different offices, which tells us that order matters. So N is equal to 16, R is equal to 4. So 16 choose 4 permutations is 16 factorial over 16 minus 4 factorial, which is 16 factorial over 12 factorial, which is 16 times 15 times 14 times 13 times 12 factorial over 12 factorial. Those cancel out, and we get 16 times 15 times 14 times 13, which is 43,680. Okay. Charity benefit is attended by 25 people, at which three $50 gift certificates are given away as door prizes. Assuming no person receives more than one prize, how many different ways can the gift certificates be awarded? Well, this is just simply how many different people can get the first door prize. Well, there's 25. How about the second? Well, now there's only 24 because somebody's already got one. And the third would be 23. So we multiply this, 4, and we get 13,800. So this brings us to combinations. We say that there again, this is a typo, NCR, combination the size of R that may be selected from among n choices without replacement or order does not matter. We can also write this combination formula into terms of factorial. NCR. N factorial over n minus r factorial times r factorial. So this here, the only thing that's different. And that's when order doesn't matter. So a group of 4 students is to be chosen from 35-member class to represent the class on a student council. How many ways can this be done? So n is equal to 35, r is equal to 4. Now, there's not positions, so order does not matter, so we're talking combinations. So we have 35 combinations of 4, which is 35 factorial over 35 minus 4 factorial times 4 factorial. So this looks a little bit different. So again, we can do the same thing here. 35 times 34 times 33 times 32, 32 times 31 factorial over 31 factorial times 4 factorial, which is 4 times 3 times 2 times 1. So the 31 factorials cross out. 4 factorial is 24. 35 times 34 times 33 times 32. I'll get 1,256,640 over 24. And in this case, you're going to divide, because we're talking about combinations. And we get 52,360. And let me just tell you at this point, if you go from here to here and you do not get a whole number, you have an error somewhere. Okay. So, what's the next one? Nope. So the United States Senate Appropriation Committee consists of 29 members, 15 Republicans and 14 Democrats. The Defense Subcommittee consists of 19 members, 10 Republicans and 9 Democrats. How many different ways can the members of the Defense Subcommittee be chosen from the 29 senators? So let's look at Republicans and Democrats. So Republicans, there's 15, and this is combinations. And we want to choose 10. And for the Democrats, we have 14, and we want to choose 9. So we have 15 factorial over 10, or 15 minus 10. 15 minus 10 factorial, and that's times 10 factorial. So this is 15 times 14 times 13 times 12 times 11 times 10 factorial. This is 5 factorial, which is 5 times 4 times 3 times 2 times 1 times 10 factorial. So the 10 factorials cross out. That's 120. 15 times 14 times 13 times 12 times 11. This is 360,360 divided by 120, and we get 3003. The only problem is I got into my Democrat area. So this is equal to 14 factorial over 14 minus 9 factorial, 9 factorial. 14 times 13 times 12 times 11 times 10 times 9 factorial over 5 factorial, which is 5 times 4 times 3 times 2 times 1 over 9 factorial. So the 9's cross out. And again, I have 120. And we have 14 times 13 times 12 times 11 times 10, which is 240240, which gives me, divided by 120, 2002. So we have 3003 ways we can do the Republicans, 2002 ways to do the Democrats. So the total number of committees is 3003 times 2002, which is a whole bunch. 6,012,006. Okay, let's skip that one. Okay, let's do the lottery here. In a certain state's lottery, 48 balls numbered 1 through 48 are in a machine, and 60 of them are chosen at random. If the 6 numbers draw match the numbers that a player had chosen, the player wins $1 million. In this lottery, the order the numbers are drawn in doesn't matter, which tells us computation. Compute the probability that you will win $1 million prize if you purchase a single lottery ticket. So we need to know how many combinations of tickets there are. So we have 48 combination 6 is 48 factorial, or 48 minus 6 factorial, 6 factorial, gives me 48 times 47 times 46 times 45 times 44 times 43 times 42 factorial over 42 factorial. I got 6 times 5 times 4 times 3 times 2 times 1. Well, I know this is 7. Dang it. 720. This cancels out. And let's see what happens there. 48 times 47 times 46 times 45 times 44 times 43. And I get 8, 8, 3, 5, 4, 8, 8, 6, 4, 0. Divide that by my 720. And I get there are 12,271,512 combinations. How many winning tickets are there? One. So the probability of win is 1 out of 12,271,512. This is something you're going to want to be sure you understand. Our project relates to this type of problem. Okay. In the state lottery from the previous example, if 5 out of 6 numbers are drawn and match the numbers that a player has chosen, the player wins the second prize of a 1,000. Compute the probability that you win the second prize. So now we know how many totals. We know how many different combinations there are. Now we need to know how many ways we can get 5 out of 6. So we have 6 possibilities, and we want 5 of them. So that's 6 factorial over 6 minus 5 factorial, 5 factorial. 6 factorial, that's 1 factorial. That's 5 factorial, so this is 6 times 5 factorial over 5 factorial, or 6. Now, the other thing we have to consider is the 6th number. Now, the 6th number cannot be one of the 5 that we got correct, plus it cannot be the 6th number that was called. So we essentially have 42 numbers that it could be, and we want one of them. So this is 42 factorial over 42 minus 1 factorial, 1 factorial. So this is 42 times 41 factorial over 41 factorial, which is 42. So the number of possible ways we could win this would be 6 times 42, which is what, 252. So a probability of second prize is equal to 252 over 12271,512. So compute the probability of randomly drawing 5 cards from a deck and getting exactly 1/8. Okay, so there's 5 things we have to look at. Get ace, non-ace, 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 ace, non-ace, 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 ace, non-ace, 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 ace, non-ace, and non-ace, 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 ace. We have 5 ways we can do this, but the probability of any of these are going to be the same. So we can simply multiply the probability of any one of them times 5. So what's the probability of the first card is an ace? Well, the probability of first card is an ace is 4 out of 52. Now, we've taken one card out, and it's an ace, so there's only 3 aces remaining, which means there's 48 non-aces, and 47 non-aces, and 46 non-aces, and 45 non-aces. Oops. So if we multiply this out, 4 times 48 times 47 times 46 times 45, we get 205476480. And then 52 times 51 times 50 times 49 times 48. And we get 311875200. That's pretty messy, but we'll leave it like that. Compute the probability of random drawing 5 cards from a deck and getting exactly 2 aces. So this is done the same way. We're looking at, we could have ace, ace. So let's do this way. 5 cards and we want to choose 2 of them. 5 factorial over 5 minus 2 factorial 2 factorial. So we have 5 times 4 times 3 factorial. 3 factorial and 2 times 1. That cancels out. We get 20 over 2, which is 10. So there's 10 possible ways we can get exactly 2 aces. Now what's the probability of getting 2 aces? Well, probability of getting 2 aces, well, we could get the first one an ace, and the second one an ace. The probability is going to be the same no matter what order they come in. Then we have 48 cards left out of 50, or 48 non-aces, 47 out of 49, and 46 out of 48. What was that bottom? Something huge. 311875200. 311875200. All right. Yes. And now we just do our 4 times 3 times 48 times 47 times 46. We got 1, 2, 4, 5, 3, 2, or 3, 1, 2. And that is it. Okay. Suppose 3 people are in a room. What is the probability that there is at least one shared birthday among these 3 people? Okay. So we got 3 people. What's the probability that the first person has the same birthday as the first person? Well, 1. We're certain of that. What's the probability that the second person has the same birthday as the first person? Well, that's 1 day, and I guess we're doing leap year since it's 2020. That's 366. Now, what's the probability that the second person has either the first person's birthday or the second person's birthday? Well, there's 2 possibilities, right? Or 365, which is 2 over 1,33590. So, suppose 5 people are in a room. What is the probability that at least one shared birthday? So, 1. We have 1 over 366. Then we have 2 over 366. Then we have 3 over 366. And then we have 4 over 366. And this becomes 24 over a whole bunch. 1794420,994, and there's one more digit that my calculator isn't showing. So that brings us to this next one here. Suppose 30 people are in a room. What is the probability that there is at least one shared birthday among these 30 people? Now let's do this. I know I normally say don't bother, but let's do this and find a decimal. This is really small. 0.000000. 14971180048. That's what that is. And this is 0.13374787779. So it's getting smaller and smaller, but there's an interesting thing. At some point, the probability starts getting larger. And this 30 people thing, it's magic. Normally what I do here is I actually look and see if there's any shared birthdays in the classroom. And I've been doing this class. This is my 4th year doing this class. And only once in that time has it not come out that there was a shared birthday. And that class only had 25 people. But how this works out to be, I'm not going to show it because it's very long. It's something like 0.72. So next time you're in a large group, do this experiment and see. Find out if there's anybody that has a shared birthday. You can even use it as a kind of party trick if we can ever have parties again. But essentially, if there's 30 or more people in a room, there's a 72% chance that 2 of them have the same birthday. Now, not the same year, of course, the same day of the year, June 5th or whatever. Maybe I'll set up a discussion and see if it works out. Okay, our last concept in this chapter is expected value. The expected value is the average gain or loss of an event if the procedure is repeated many times. We can compute the expected value by multiplying each outcome by the probability of that outcome, then adding up the products. So, in the casino game roulette, a wheel with 38 spaces, 18 red, 18 black, and 2 green, is spun. In one possible bet, the player bets $1 on a single number. If that number is spun on the wheel, then they receive $36. So their original dollar plus 35. Otherwise, they lose their dollar. On average, how much money should a player expect to win or lose if they play this game? So, what is the probability of winning? Probability of winning is 1 out of 38. So, what's the probability of losing? Well, the probability of losing is 37 out of 38. So, if you win, what do you get? $36. If you lose, what happens? You lose $1. So, if you win, the expected outcome here, 36 over 38, or negative 37 over 38. So if we add these together, we get negative 1 over 38. Which, if we figure that, 1 divided by 38, how do we get? Roughly 0.026. So basically 2.6 cents, and that's a negative. So now you see why casinos have all that glass. The games are rigged for you to lose over time. And how many people play roulette? 2.5 cents times hundreds of thousands of people can be a lot of money in a short period of time. Okay. Now we're back to this lottery again. 48 balls, 1 to 48. Place the machine. 6 are drawn. 6 numbers drawn match the number that the player has chosen. The player wins a 1 million. 5 numbers match, and they win 1,000. So let's go back and get our numbers. We need the probability of winning. Where is it? Up here somewhere. Where's the lottery one? There it is. Probability of winning. I get this number. And this problem here is definitely one you're going to want. So technically, if we win the 1 million, we're really only winning $999,999. Probability of that is 1 over 12,271, 512. 999, 999. We'll go ahead and multiply this. What you win divided by or times the probability. So that's this. Now the probability of winning a style, well, it's $999. Again, it was over to 1, 2, 2, 7, 1, 5, 12. And how many were those? $252. 252. Multiply that by our 9,999. What do we get? 52 times 9,999. And we get 2519748 again over 12271. Now this is exactly what the project is, except more detail. And we'll get into that in the next recording that I make. So what about the probability of losing? Well, that's negative $1. And what do we have? We have 1 plus 252 winners. Subtract that from our total number of tickets. So we have 1,227, 1,260, and that's over our 1,227,1,512. And that's times negative 1. So I'm just going to do this. And then I'm going to add all three of these up. Plus 2519748 plus 999,999. And I end up with negative 8751,513 over 12271,512. There's 6 there. So we'll go ahead and divide this so we can convert it into money. And this is equal to negative 0. roughly 71 cents. So what does this mean? Well, essentially it means that if you were to buy all 12,271,512 tickets, you would lose an average of 71 cents a ticket. And this is how lotteries make so much money. Okay, now that we've talked about how the lottery makes money, let's talk about insurance companies. A 42-year-old man in the U.S., or 40-year-old man in the U.S., has a 0.242% risk of dying during the next year. So let's convert that to a decimal. Move the decimal place 2 places. 242. As an insurance company charges $275 for a life insurance policy that pays $100,000, what is the expected value of the person buying the insurance, or for the person. So subtract that 275, so multiply this times the payout, $99,725. And then also 0.99758 times negative 275. And if we don't die, well, that's what we'll get. So what's this? 0.00242 times 99725. And this is 241.3345. Take this, 0.99758 times negative 275. And we get negative 274.3345. So essentially minus $33. And that's how the insurance companies make their money. They calculate the probability of you dying. They have people that do that. They have a whole field of statistics that's just designed for that. They take and calculate what their expected loss is based on the probability of your death and the payout. And then they decide how much profit they want to make from you, and that's how they adjust it to get your premium payment. So this is it for the probability chapter. Again, after this chapter, after you're familiar with it, we'll look at project, the only project we're having. And as I said, it's the lottery. If you've looked at it, you'll see. And we'll go, I'll probably give a brief lecture on that. You guys will have it as well.